Thank you for the introduction. Today I'm going to talk about quantum error correction for noisy Hamiltonian estimation. And this is a joint work with my former master student, Santanu. And he's currently a PhD student at Yale. So I'll start with an outline of this talk. So I'll first give a basic introduction to quantum metrology or quantum estimation theory. And then I'm going to talk about the effect of noise in quantum metrology. And then I'm going to discuss how quantum error correction can be useful for quantum metrology. Finally, I'm going to introduce our recent work on stabilizer code for three-body Hamiltonian estimation. So as you will see, since most people consider quantum error correction in the context of quantum computation, and you'll find out there are some fundamental difference between thinking about error correction for metrology and error correction for computation. Okay, so first, let me motivate, like, why do we want to study quantum metrology and what is quantum metrology? So quantum metrology is basically the science of estimation in quantum system. And here are three basic examples. The first one is gravitational wave detection. You use some optical interferometry to try to detect the difference between two optical paths, and that one would be the unknown parameter in the quantum system you try to estimate. And then the second example would be atomic clock. You have a bunch of cold atoms, and then you try to use them for whether entangled or not to detect the laser frequency. And there can be other examples like using nitrogen vacancy centers to detect electric field or magnetic field, and so on. So to introduce some basic concepts in quantum metrology, I'm going to start with the simple but a very important example, which is a single qubit phase estimation. So in this example, I'll start with a single qubit state as this plus state, which is superposition between 0 and 1. And then I'll have a Hamiltonian evolution governed by the Pauli Z rotation. And then the angle of this Pauli Z rotation theta would be the parameter we try to estimate. So the output state would be a function of theta. As you can see, the information of theta is encoded in the phase difference between 0 and 1. And then afterwards, what you do is, you basically do a Pauli X measurement, like project the state onto plus state and minus state. And you will see that the expectation value of X in this situation would be cosine theta t, which is a function of theta, the unknown parameter you try to estimate. So, So here I'm showing the plot where the horizontal axis is theta, the unknown parameter, and the vertical axis is the expectation value of X. So you can see that basically by estimating the expectation value, you can infer the value of theta from the relation between these two. And clearly the slope of this function is going to determine your estimation precision. So you have this error propagation formula where you can try to see that the estimation error of theta is determined by the estimation error of X and the derivative between these two numbers. So in fact, you can have a rigorous statistical lower bound given by the so-called quantum Cramér lower bound. It says the variance of estimated theta is going to be lower bounded by 1 over f, where f is the quantum Fisher information. And the expression of the quantum Fisher information is exactly given by this error propagation formula. So it is basically the derivative of x with respect to theta square over the variance of x. And in this particular example, x is actually the optimal observable here. So basically, it is the observable that maximizes this expression of the quantum Fisher information. And there are two important parameters I'm going to point out here. The first one is we notice that this quantum Fisher information is going to be linear in the variance of h. H is basically the Hamiltonian you try to estimate. And you can see that the larger the variance of h is in the quantum state, the more sensitivity you have of this quantum estimation task. And then the other parameter is the scaling with respect to the sensing time. So here you can see that the scaling is quadratic. And this is the so-called Heisenberg limit. And in fact, this is the best limit you can observe using this type of single qubit Hamiltonian rotation experiment. Okay, so and another thing I'm trying to point out is that this quantum Fermat lower bound is not only a lower bound, it's actually searchable in the asymptotic sense. It means that if you just repeat the same experiment many times, then the estimation variance is going to be scaled as 1 over n times f, where f is basically the quantum efficient information I introduced here. And finally, you can interpret the notion of quantum efficient information using the notion of fidelity. So the infidelity between a quantum state at theta and a quantum state at theta plus d theta would have a second order derivative, which is roughly 1 over 8 times f, where f is efficient information. Okay, so now I'm going to move on to something more interesting, which is the multi-qubit phase estimation. So I'm going to start with the simplest case, where you basically just have a product state as an input. And in this case, you can find out that the Fisher information is going to be additive. That means the Fisher information is simply n times t. And you can interpret that as you just flip the same coin n times, and then the variance would be 1 over n times the single shot variance. And then this type of scaling, I'm going to call it standard quantum scaling here. So it is like linear in n, and it can actually be overcome if you have like entangled input state, which is shown on this slide. So in this case, I no longer have like product input state, and I'm allowed to use like an entangled input state over n qubit. And in this situation, I'm going to use this GHD state, which is actually the optimal input state you can use. You can see that the phase is going to accumulate n times faster than the previous situation. And if you calculate the quantum efficient information in this case, which is going to be given by the parity observable x tensor n, and in this case, the Fisher information is going to scale as n squared. So it is better than the previous standard quantum limit scaling. And this is, in fact, the best scaling you can get in this scenario. And I'm going to call this Heisenberg scaling. So basically, in my talk, I'm going to use scaling to talk about scaling with respect to the number of qubits, and the limit to talk about the scaling with respect to time. So both are very important in this discussion. Okay, so perhaps even more interesting is what happens if you have not only like one local Hamiltonian, but some kind of interaction in your system. And the dynamic itself can generate entanglement in your system. And a standard model people usually consider is this fully connected K-boundary interaction. And here I'm just considering this Pauli-Z interaction for simplicity. So in this case, the Hamiltonian is theta times the summation of all weights K tensor of Pauli-Z. And you can find out that in this situation, the optimal scaling would be n to the power of 2k if you are allowed to have an arbitrary input state. And even if you can only have product input states, the optimal scaling would be n to the power of 2k minus 1. So, and in both cases, we say we achieve the super Heisenberg scaling. It's basically some kind of scaling that is better than n squared. Okay, so just to summarize a little bit here, we consider two types of estimation limit. The first one is with respect to probing time, and the second one is with respect to the qubit number. And if you have a product with an input, I think this one is a bit, okay, I think I got the, maybe we can just forget the first table because this will be clear later, and I think this table is wrong, but basically we can look at the second table here. So the second table here is we have the product with an input, and have a local Hamiltonian, then the scaling would be standard quantum scaling, which is the situation where the Fisher information is proportional to n. And then if we have an entangled state, then we can get to the Heisenberg scaling, n squared. And in the situation where we are allowed to have like k local Hamiltonian, then we are allowed to achieve the super Heisenberg scaling. So if you just put k equal to 1 here, we just go back to the first row here on the second table. Okay, so now I'm just going to put noise in the setting. So in the situation where you have noise, in this case, I'm considering this simplest dephasing noise. That means you have this Pauli Z rotation, but then you also have some dephasing noise in the situation. And then you still consider the optimal input state in the noiseless case, which is the GHZ state, and the product of plus state. And you can see that the Fisher information is going to still have a coefficient that scales like n squared t squared, but then it is decaying exponentially with a coefficient proportional to n times t. So in both cases, you can calculate this quantity, which is the average Fisher information per time. And you can see that this number is going to be only linear in n. So you no longer have the Heisenberg scaling anymore. And in fact, that basically means in the noisy situation with these two types of inputs, you can only achieve the standard quantum scaling and the standard quantum limit. So again, by scaling, I mean the scaling with respect to the cubic number, and by limit, I mean the scaling with respect to time, both of which I'm trying to optimize here. Okay, so, and then the natural question in this situation is, what we can ask is, can quantum error correction help in this situation? And now I'm just going to briefly talk about some general rules about applying quantum error correction in the situation of quantum metrology. But before that, I'd like to ask if there's any question here. Okay, so if there's no question, I'm just going to introduce the condition of quantum error correction in quantum metrology. So the setting is shown on this diagram here. So I'm going to consider a noise evolution of the quantum system governed by some Hamiltonian evolution with strength theta, which is the parameter we try to estimate. And then there's also this Lombardian evolution, which is parameter independent, but something exists in your system. And what we can do is we can apply quantum error correction throughout the evolution of the system. So there are two very important and very strong assumptions here. The first one is we are allowed to have a bunch of ancilla, which is free of noise. So that assumption seems artificial, but basically you can think of them as some noisy probe after you do some first layer of quantum error correction. And then again, like we assume like this ancilla is noiseless, and all this quantum error correction control is noiseless. So basically, we don't consider any fault tolerant situation in this case. And then the other example is we can do the control very fast in a frequent manner. So that means we can allow the system to evolve for amount of time dt, where dt can be very small. And we consider a limit where dt is very small. So under these two assumptions, there's a criterion that can be derived, which tells you a necessary and sufficient condition on determining whether or not you can achieve the Heisenberg limit or the Heisenberg scaling. So the condition states that the Heisenberg limit or the Heisenberg scaling is achievable if and only if the Hamiltonian is not in the Lingba span. So let me explain a little bit here. So Hamiltonian here is simply the signal we try to estimate. So we just try to estimate the strength of this Hamiltonian. And this Lingba span here is kind of a noise band in your system. And if anyone is familiar with Kniaev-Laflamme condition, it is basically the operator that appears in the Kniaev-Laflamme condition in the Lingba equation. And the statement that Hamiltonian is not inside Lingba span is necessary because you want the error correcting code to correct everything in your Lingba span, but also preserve some non-trivial contribution by the signal Hamiltonian. So to see a very simple example, again, the single cubic phase estimation case. If your Hamiltonian is a Pauli Z rotation, and then your Lingba operator is also a Pauli Z rotation, you can easily see that by this condition, the HNLS fails, and you can no longer achieve the Heisenberg limit or the Heisenberg scaling. And what's more important is that even if you have this most powerful control, you cannot get rid of this dephasing noise without jeopardizing the performance of parameter estimation. However, in the situation where you have like Lindblad operator X, that means you have bit flip noise. In that case, you can design something like a repetition code. And in that case, you can show that the quantum error correction can actually recover the Heisenberg limit or the Heisenberg scaling if you perform the quantum error correction sufficiently fast and precisely. So to see how that works, basically, we can always show there exists some quantum error correcting codes that satisfy these two criterion whenever the HNAS criterion is satisfied. So the criterion is basically the Kneel-Laflamme condition in the Lindbladian case, but with an additional assumption, which is the projection of this Hamiltonian is not going to be a trivial operator in the logical space. So basically, that has to act non-trivially in logical subspace so that we can detect this signal in your logical space. And if you look at this master equation over here, basically after you do error correction and do the perfect decoding afterwards, you are going to have this error corrected master equation where you just have this unitary evolution, and then the Hamiltonian is going to be this logical Hamiltonian PHP in the situation. So what's puzzling here is that in order to construct this quantum error correcting code, you actually usually or generically you need the assistance of noiseless ancilla. So you cannot just create an ancilla-free error correcting code in your code space. And then moreover, it is solvable via the semi-definite program. So basically, there's no easy way to solve it if you have a very large dimension of the system. So, and also this code does not come in the stabilizer formalism, which is the most common formalism people usually use in quantum error correction. So now we can ask the question, can stabilizer code help in this case? And this brings us to this final section of my talk, which is the stabilizer code for three-body Hamiltonian estimation. And please ask a question at this stage. S is basically any operator in the noise or Lindbladian span. So we basically try to make sure it is trivial in the logical space so that it can be corrected. Please.
The collection of qubits is a probe, right? So
yes.
And apparently you want to collect signals as long as possible.
Yes. Yes.
With the source.
Uh-huh.
How does this work together with the integrating the error correction?
So I think it's okay. So even though here I'm saying that you have to do error correction like infinitely fast, but I think as long as it makes sure the error does not propagate to anywhere in the system, physically it is smaller than the rate of the noise, then it should be fine. So, but I understand this is a very strong assumption, but I would say it is important to understand even in this limit, what can we do with quantum sensing and error correction. Thank you. Okay, so in this final case, I'm going to consider this concrete example, which is the situation where you have the Hamiltonian that is weight 3 interaction of Pauli Z operator. And I'm going to consider some Lindbladian, which is given by basically any single qubit operator, which means in that case, the Lindblad span is going to be the span of any weight 2 operator. And that makes sure the HNLS condition is satisfied because the Hamiltonian is weight 3 and the noise is only weight 2. And I guess an additional bonus point we have here is we are also allowed to remove any two-body Hamiltonian interaction in the system. So the reason is that if we put the projection onto the system, the Hamiltonian is going to be PHP. And then if we have any two-body interaction, that is just going to be like trivial in the logical space. So we cannot detect them. And that means we also erase them from the Hamiltonian evolution. So basically, in order to correct these single qubit errors, we need to do active error correction. But then basically, if we just try to erase some coherent to local Hamiltonian, we just need to keep project the system onto logical space. And that is simply like quantum Zeno effect. Okay, so now we have this important lemma to help us understand how stabilizer code can be useful for sensing a three-body Hamiltonian. And it basically says that if we have like a distance 3 stabilizer code with one logical qubit, and in this case, I'm going to use the number L to represent the number of a Z tensor 3 logical operator. So that it is essentially any operator that can be written as Zi, Z, J, Z, K, and is also a non-trivial logical operator in the system. And then you can see that in that situation, we can achieve the Fisher information that is quadratic in L and quadratic in T. So why is that? Basically, after we do the projection of the Hamiltonian, everything is going to be trivial. If we have some kind of error operator, then it's just going to be like contribute to 0 to the logical Hamiltonian. And if we have like some stabilizers, that's just going to be an identity. So the only thing that remains is going to be the logical operator that is non-trivial in the system. And another thing is here, since we are considering only one logical qubit, we just need to make sure like every logical operator corresponds to the same logical gate. For example, here I just use ZL for simplicity. And that is easy to achieve because clearly like all Z tensor 3 operator commute with each other. And also we can easily make sure they have the same sign, because we can just make sure all Z type stabilizer have the positive sign. And in that case, the logical Hamiltonian in the logical space is going to be just be L times ZL. So, and we can just use the single qubit estimation result, which gives us the Fisher information equal to 4 times L squared times T squared. So everything just boils down to counting how many Z3 logical operator exist in our stabilizer code to determine whether it is going to be useful for the three-body Hamiltonian estimation. So first, there's a very simple example, which is the thin surface code. So in this scenario, we can see that the number of these three logical operator is just linear, because the only weight 3 operator that contribute non-trivially to the logical operator is going to be this a vertical line here. And the number of them is going to be linear in the number of qubits. And as a result, the Fisher information is going to be n squared times t squared. So you can see that we achieve the Heisenberg limit with respect to time, and we also achieve the Heisenberg scaling with respect to the number of qubits. However, we do not achieve the super Heisenberg scaling in this case. That means Fisher information is, that means surface code is only suboptimal in this scenario. And the second example I'm considering is this quantum Reed-Muller code. So it is basically a code that is defined from the classical Reed-Muller code, the shortened classical Reed-Muller code. And the code word is given by this degree 1 Boolean function, polynomial. And you can actually count the number of weight 3 Z logical operator using like the McWilliams identity, and you are going to see that it is like quadratic in N. So it performs better than the surface code. And as a result, the Fisher information is just going to be the square of it, which is n to the power 4 times t squared. So again, you achieve the Heisenberg limit, you achieve the super Heisenberg scaling, which is very nice. But this is actually not the optimal we can do here, because from the previous result, we know that if we have like a k-body interaction, then the best scaling we can achieve is n to the power of 2k in a noiseless scenario. But actually with noise, we can still do that. So actually the best code in this scenario is the short code. So it is simply like this tensor product of 3 GHZ states. And the reason that it is particularly good for sensing the three-body Z interaction is because there are actually many Z3 logical operator. So it is because if you just pick any Z operator in the first block, and any Z operator in the second block, any Z operator in the third block, and combine them together, it's going to be a logical operator, logical Z operator in the code. So basically, it means that you can have like n cube number of logical operator in your shortcode. And then this is actually the best scaling we can get. In this situation, the efficient mission is going to scale as n to the power of 6. And that means we not only achieve the Heisenberg limit, which is the best thing here, but also the optimal scaling with respect to the number of qubits. So, okay, what I just said before might be a bit artificial. I just show like 3 examples of code, and each of them correspond to different scaling of the Z3 logical operator here. And we can actually show some result from the other direction, basically. There are certain conditions that needs to be satisfied in order to achieve certain type of scaling here. So actually we have like 3 necessary conditions. The first one gives you basically what we must do to go beyond linear scaling. So again, linear scaling corresponds to this surface code. And the statement of theorem is like, if there exists some sort of stabilized generator such that its highest weight is like below W, then L, which is the number of Z3 logical operator, is going to be at most some constant times W squared times N. So this basically rules out any possible performance beyond thin surface code with like other type of like LDBC code. Because if we have a LDBC code, then W is a constant, and then L would be basically the optimal, the linear scaling would basically be the optimal scaling we can get. So we can not achieve super Heisenberg scaling with LDBC code. And so why is that the case? The idea is basically to notice that if we have too many Z3 logical operator, there will also be too many Z2 stabilizer, because if we just consider the product of 2 Z3 logical operators, sometimes they generate some Z2 stabilizer, and then they can violate this weight assumption. So here I'm just showing one example. And I'm fixing 2 qubits here. The first qubit is qubit 1. The second is qubit I1. And the thing I'm going to consider as a variable here is the index of the third qubit. So it can be here like I2, I3, I4 until like IW plus 2. And you can see that if all of this operator, which correspond to the red line here, are the non-trivial logical operator, and then the product of each of them is going to be a stabilizer. And in that case, you basically have like a large weight stabilizer generator, which goes from I2 to IW plus 2, and that leads to a contradiction. And so basically using this type of technique, you can show that you can no longer go beyond the linear scaling if the highest weight is a constant. So another result corresponds to what we must do to achieve the quadratics, to go beyond the quadratic scaling, is that if we don't have any Z2 type of stabilizer, we can not have anything beyond the quadratic scaling. So that simply means the quantum Riemann code is actually the optimal thing we can do in this situation, because it is a type of code that does not have any Z2 stabilizer, but it actually achieves this n squared scaling on this restriction. And to prove this result, again, you just need to use the fact that the product of 2 Z3 logical operator is going to be a stabilizer, and this assumption simply means that they do not share any weight to support. And you can just do a simple counting and show that the optimal scaling you can get is n squared. And the final result is probably most surprising, is that if we want to achieve the optimal scaling, which is a qubit scaling here, there must exist a large number of qubits whose number is linear in n, such that we have a stabilizer like Zi1, Zi2, Zi2, Zi3 until the end. So basically that means we must have some kind of repetition code structure if we want to achieve the optimal scaling here. So certainly like short code is an example, and clearly this is something we must have. It's not just like coincidence. And in order to show this, we just need to consider the same type of graph where we just fix the first qubit to be qubit 1, and consider the edge between qubit 2 and qubit 3, where they form a logical operator. And then we can show that this type of graph must be an almost complete graph. And then using that result, we can show it must have some kind of repetition code structure in order to get the almost complete graph assumption. Okay, so yeah, maybe I'm just going to summarize here and take questions afterwards. So basically what we show in this talk is stabilizer code are useful for three-body Hamiltonian estimation. And clearly the performance depends on the structure of the code. And clearly there are like many open questions. For example, what happens if you have higher order interactions? Or you put some restriction on the geometry in the local Hamiltonian simulation. And also, what happens if we don't just want to estimate the strength of the entire Hamiltonian, we just want to estimate different parameters correspond to different terms, which gives you this multi-parameter estimation problem. And finally, since we have this very strong assumption about doing very fast and perfect quantum error correction, and we can ask what happens if we remove some of these assumptions. And yeah, that's all. Thank you for listening.
Can you say something about like what context you would want to do three-parameter estimation in? Like what kind of scenarios would this be useful?
Yeah, so I would imagine like so first the motivation to study three-body is basically because this no-go theorem, since like any one-body and two-body is not going to be robust against like any single QB error. So I would imagine it's basically you have some kind of strong interaction in your system, like involve some kind of three-body interaction, but maybe you also have some one-body and two-body interaction you try to get rid of. And then you can just use this protocol to basically make sure all of them perform trivially in a logical space, but then you just have a remaining three-body interaction and you can estimate that. But since like actually like I don't know much about quantum matter, so maybe this type of three-body interaction does not exist often. I don't know. I just in the situation where that exists, I would imagine this type of protocol to be useful.
Great. Thanks.
Okay. So maybe this is related. Like, I think maybe I just missed it. Like, so you said this is robust against two local Hamiltonian terms. Like, if you have unknown one local Hamiltonian terms, is also okay, or?
Yes. So basically, the framework is that after you do error correction, like all one-body and two-body term is going to be like act trivially in the logical space. So all you have is the three-body term. So. Yeah.
I see. Yes, that makes sense. Thanks. And maybe another question is like, do you see this works for like non-commuting terms in the Hamiltonian?
Yeah, I think it can work. It's just not going to be as simple as this case, because like in our discussion, basically we just assume like every operator is like the same logical operator, but then if you have like non-commuting, they must correspond to different logical operators. So you can still detect them somehow, but you're not going to have this like maybe you don't have this L-square scaling, but you can have some sort of non-trivial thing in your logical space.
Okay, thanks.
Yeah.
Other questions?
Can you relate this to Inst theorem? I think I just missed your setting.
Oh, so I think, yeah, okay. So I'm not sure like if there's any direct relation to async new. So basically, I think one part that is related to async new is that, for example, here if you have some kind of like a single qubit noise, and then your Hamiltonian is also like one local, I guess that corresponds to the async new setting, which is the transversal gate. And then in that case, this theorem can actually be used to prove some similar statement as the async new. So basically, the fact that we cannot get the Heisenberg scaling with this single qubit noise, and one local Hamiltonian is going to be closely related to like this Inst theorem where transversal partial gate cannot be universal. And that is essentially why we're considering this higher order term, which is this three-body Hamiltonian. So basically, for like one-body term, like you cannot get any advantage in sensing, and then that is closely related to Inst. Like I have some like 2 papers in that direction. Maybe I can show you later, but that is not exactly related to this talk.
So can I summarize what you just said by saying that you're looking at the Hamiltonian whose operators are the logical operator of a code?
Sorry, can you repeat again?
Is your operators in the Hamiltonian logical operators of a code?
Yes. So basically, this is like counting how many terms are logical operator of a Hamiltonian. And if the number of terms is large, that means you can sense them better. So that's the message here.
Further questions?
So, looking at that Hamiltonian, assume that's a sum over all triplets of sites. Mm-hmm. That looks like it's, I guess, most of the Z cubed operator, if I take the Z component of all the qubits, add it up and cube it, right? Yeah, so exactly. It has the feeling of one big spin, mm-hmm. right? Is that a good intuition? Like, is that a kind of, as you generalize to maybe more than 3 bodies? Is that
I think that's actually like the very good intuition. And I think that this may be why considering surface code is no different from considering like other type of LDPC code, because the thing you try to estimate is basically this one big spin. Yeah.
Okay, any last questions?
Okay, if not, let's thank Sisi again.